In this video, I will be giving a quick demonstration of the Nengo workspace and showing some model construction methods. Let me begin by dragging an empty network and putting some neurons inside of it. I won't be worried about the function of this particular network. So let me just get started by having a population of neurons that has an input, where the input function in this case is just going to be a sine wave and a constant in two different dimensions. Now, this network can actually be run directly inside Nengo, although we usually prefer to use interactive plots. Running within Nengo can be accessed from going to the File Run Network menu and setting a start time, a step size, and an end time. And typically we like to see the data viewer, which shows us the results of the simulation afterwards. Before we do that, in fact, we have to say what data we would like the data viewer to collect. So we can go inside each population and pick some random neurons if we'd like to probe, for instance, their membrane potential. Some of what I'm doing is going off screen here because of the small screen size for recording this video. But if you right-click on any item and go down, you can see an Add Probe, and there are various things to probe. So for the neuron that I just selected, I probed the voltage, and for this population, I'm just going to look at the encoded variable from the population of cells. I can now run this population by selecting File Run or hitting Ctrl-R and saying OK. The simulation then runs and data has been collected. So we have data from a single neuron, which we can look at. Here you can see the subthreshold voltage and various spikes being generated. Or we can look at the data from the entire population and see that one of the dimensions is in fact encoding a sine wave and the other is holding constant at about 0. One reason this is interesting to see is because we can in fact go and change the way that we simulate a particular population of cells. So for instance, if we select the A population and go to the top of the Nengo workspace, we can choose to simulate it as rate neurons instead of spiking neurons, or even in what we call direct mode, which is very rapid, but in fact does not simulate the neurons themselves. It only simulates the function that the neurons are trying to compute. So if we again run this simulation in direct mode, we can see that it's done very fast, and if we look at how the neuron population should act, we can see, oh, they're supposed to reproduce both a flat line and a sine wave. This is often useful when we have many different populations in a network model, and we would like some of them to be simulated accurately, and others we are less concerned with in order to save simulation time. Each of the objects in a Nengo simulation has many properties that we can access using our inspector. In the top right, we have a magnifying glass. If we select that, we then see the inspector, which has various bits of information about this particular object. So we can have things like documentation, the kinds of functions that are in this input function, or if we look, for instance, at an input synapse, we will have information like the dimension of the synapse, the transform of the synapse, the time constant of the synapse. And similarly for the neurons, we will get information like the name of the population and information about each individual node as well if we want. This can occasionally be useful to edit on the fly. For instance, we have 100 neurons in this population, but suppose we would like more accuracy. We can increase the number of cells by typing 120, and when we hit return, the original population we had was now replaced by a population of 120 neurons. You can see that isn't updated here, but if we close the window and reopen it again, we can see now that this population has 120 nodes in it. Moving right along, let me make this network slightly more complicated in order to demonstrate two other features of Nengo. So I will draw up another population of neurons in, let them be the same as before. You can notice that if I attempt to reuse a name, Nengo will ask me for a different name. Similarly for terminations. Now I've created a communication channel with two populations of cells. Now, if I have these populations in a sort of disarrayed manner, this button called Layout at the top, when we select one of the populations and click Layout, it will attempt to put the network in a somewhat feed-forward manner and then fit it in our view. This can be useful when we have large, complicated models that we are loading from scripts. Next, I'd like to demonstrate a reasonably unique feature of Nengo, which is represented by these three connected neural populations in this icon. In Nengo, as in most neural simulators, when we construct connection weights between two populations of cells, those weights can be either positive or negative. However, this violates what is known as Dale's principle in biology, This is the idea that neurons are either excitatory or inhibitory, not both. What we can do in Nengo is we can select a particular input termination and then click this icon. What it will do is introduce some number of interneurons that we can define. And those interneurons are now connected in such a way that they only have weights of one sign, and in addition, the connection between the populations now only has a weight of one sign. In sum, these three populations now compute the same function that was being originally computed by the two populations, but it is doing so in a much more biologically plausible manner. The final feature I would like to discuss in this tutorial is how to connect multiple networks together. Currently we have a single network, but often it is convenient to have many subnetworks which are then interacting. Let me construct another network and place some neurons inside of it. And now what I would like to do is connect these two networks to one another. In order to do so, I still need to define an input into the population of neurons, which is receiving input out from outside of the network. But now what I must do is right-click on that particular input and say Expose Outside Network. I then provide a name, I will just call it Input, which will be a name which is visible outside of this network and that other networks or populations can connect to. You can see now the network itself has an input termination. In order to connect something to that, I need to expose one of the outputs from the original network I had, the demo network. So I will select this output, right-click on it and say Expose Outside the Network. I will give it a name. And now I have an output and an input, and it would be nice to connect them together. However, in Nengo, the highest level object must always be a network. So I must introduce another empty network. And now I need to take each of these previous networks I constructed and place them inside that network. Do this by simply dragging and dropping. And now, because both of these subnetworks are inside of another network, I can connect them directly to one another. Constructing this kind of hierarchical model is extremely useful when we get more sophisticated sorts of models in Nengo. I should note that it is actually quite simple to select multiple objects in Nengo as well. If one simply holds down the Shift key, we can see in the bottom right that we change from navigation mode to selection mode, and then we can select multiple objects in order to move them together, for instance. It's also possible to save whatever view we currently have in the workspace as a PDF for sharing or publication by clicking the Save as PDF button and saving the file. I should note in conclusion that when constructing sophisticated models in Nengo, we often do not use the graphical user interface. This is because much more detailed control can be had by scripting. We can open such scripts, which are written in Python, into the graphical user interface, and we will see a model that looks much like one that we might have constructed by hand. For example, I am opening a basal ganglia model here, which has a main network and several subnetworks that you can see. If we click the layout button, these will be organized for us in a standard kind of basal ganglia feed-forward model. I should also note that we typically do not run simulations using the file run method, but instead use interactive scripts. I will show this in more detail in the next video.